Alright, so the second part of the bookwork here has three more gas laws. The first one is the combined gas law. And in this situation, we can have the pressure, volume, and temperature all changing. Now in the book, they might show you the equation again as P1 V1 over T1 equals P2 V2 over T2. And that's fine, but as I said before, when you have to do this setup, then you're going to have to eventually cross multiply, which is why I usually set it up the other way. P1 V1 times T2 equals P2 V2 times T1. And so that's another option of the equation you can use. Now again, rule of thumb with these gas laws, I really think you should always look and change temperatures right away no matter what. So again, 5 degrees Celsius, to me, that's 278 Kelvin, adding the 273. 2 degrees Celsius, 275 Kelvin. So now that we see that, then again it becomes one of our plug and chug situations. We've got a balloon at a certain volume, at a pressure of 1.3 atmospheres, temperature 278 Kelvin. Double the pressure, temperature goes down a little bit. What's the volume of the balloon going to be? So plugging the numbers in the right spot, my initial pressure is 1.3 atmospheres, my initial volume 146 milliliters, and the second temperature, the temperature goes down to 275 Kelvin. The pressure doubles, so it goes from 1.3 to 2.6. The new volume is what I'm looking for, and the original temperature, it started at 278 Kelvin. Now, even though we're talking about three variables here, it still doesn't hurt to engage your brain. The temperature is not changing much, but the pressure is doubling. So when I see that and I'm looking at the volume, well, to me, adding that much more pressure, we know that increased pressure compresses the gas, so the volume's going to have to go down. So I'm looking to find an answer less than 146 milliliters. And so when I multiply both sides, then I divide by the 722.8 so I can solve for x, I get an answer of 72 milliliters. And that really does make sense. Again, temperature goes down a little, which also causes the volume to drop. The pressure doubles, so the volume should pretty much get cut in half, so 146 down to 72. So that answer makes sense to us. The next law we're looking at is Avogadro's law. And this we've worked with a little already this year, but it says 1 mole of any gas, hydrogen, helium, nitrogen, methane, oxygen, carbon dioxide, doesn't matter. 1 mole of any gas, if it is at STP, standard temperature and pressure, then it will occupy 22.4 liters of space. Our STP conditions are 0 degrees Celsius and 1 atmosphere. But remember, we can express that different ways. We don't really care for Celsius during the gas laws, so 273 Kelvin is also an acceptable standard temperature. And then to start this unit, we looked at different pressure units. 1 atmosphere is the same as 101.3 kilopascals, or 760 millimeters of mercury, or 760 torr. Or we had the same for PSI, 14.7. Yeah, that's it, 14.7 PSI. So those, 1 atmosphere. I can say hi to you in Spanish, or I'm sorry, hi in English, hola in Spanish. They both mean hi. 1 atmosphere is the same as those pieces of information. Now, as far as solving Avogadro's law questions like this one, what size container, meaning volume, do you need to hold this many moles of nitrogen gas at STP? Well, this is just our map to moleville. Okay? If you know how many moles you have, you're in moleville. You want to know the volume, that's literland. And we're using highway 22.4. So to get from moles to liters, I need to multiply by 22.4. And that's exactly what I do. Moles times 22.4, and that gas is going to need a 1.03 liter container. Well, what about mass? Well, okay, how much carbon dioxide gas in grams is in a 1 liter balloon? Okay, carbon dioxide, of course, CO2. And so again, on our map to Moleville, this time we start in liter land. We have 1 liter of gas. So we're going to divide by 22.4. That takes us to Moleville, but then we've got to get to Mass City. So we have to multiply by the periodic table. So again, using our map to Moleville that we've done since October. And so I take my 1 liter divided by 22.4, multiply by carbon dioxide, 12 plus 16 plus 16 for the 2 oxygens. That's how I got the 44. And that is 2 grams of carbon dioxide gas in the 1 liter balloon at STP. All right. Now on your foldable, if you'd like, you can put some Avogadro information and examples on the back of your foldable. But again, you can always have your map to Moleville. You can always use that, so your choice. And now the last law is the ideal gas law. And this gas law has all 4 of our variables in it. So we've got pressure, we've got volume, we've got temperature. N is the amount of gas. Moles. Can't use M. M in science is mass. And then we've got this ideal gas law constant. And so hopefully you filled out that little chart, because the constant will fluctuate depending on the pressure units. So here our sample question says 0.9 atmospheres. So R is going to equal 0.0821 when our pressure is in atmospheres. If our pressure was in kilopascals, R equals 8.314 when our pressure is in kilopascals. Those are the 2 that I mainly use. There's also an R for millimeters of mercury, and that's 62.4, but I typically don't use that as much. So again, we've got a little plug and chug situation. Here's our sample saying calculate the volume of this gas at these situations. So I got to plug in my numbers. My pressure, 0.9 atmospheres. The volume is what I'm solving for, X. N is moles, 0.323. The R, again, since I'm atmospheres, I use the 0.0821. And then temperature, be careful. This is already in Kelvin, so don't double convert it. So I just plug in the 265. Multiply both sides. Divide by 0.9 to solve for X. And then that will take us to our answer of 7.81 liters. It's a volume. And another factor of having a gas law constant, okay, since we have a constant involved, our volume must always be in liters. So make sure you know that. Include that in your foldable. The volume for the ideal gas law only has to be in liters. It can be in milliliters for others, but has to be in liters for the ideal gas law. If some mean teacher, like myself, would give you milliliters in a problem for the ideal gas law, then you have to change that to liters, and we know that that can happen by dividing by 1,000. So that's another fact that should be in your brain, or at least should make it to your ideal gas law flap on your foldable. Alright, so now you should be able to complete the practice part 2, and good luck with that.